Okay, so hello everyone. In this video I want to show you how to run the DFP models library that has been made available to you. So in this library you'll find the implementation of deep feedback in neural networks, and we currently have the three types of ResNet and the DeepLab v3. We are looking for contributions on the vision transformer, so please feel free to make contributions to this repository. This is exactly the code that we'll go through today, okay? And yeah, so we have a homepage where we explain this research. You also have the paper associated to this research, so please feel free to check this. And yeah, okay, so the example that we'll be running today is an example on the MNIST dataset. So the first thing that you'll need to do is to go here to this repository and install the deep feedback models package. This is already installed, so I'm not going to do this, okay? And what we are going to first do is import the important libraries for this example. So we are going to import PyTorch, Torch Vision, and we are going to run a ResNet. So we are going to go to the DFP models package. This package has three main branches that describe it, so the state, the equilibrium, and the models. And it's in this folder of models that you'll find the different architectures that have been developed. So we're going to go to models and we are going to import the ResNet 18. So this ResNet 18 is going to have the implementation of a ResNet 18 with feedback from the layer 4 to the layer 1. So just run this. Then we are going to start defining the training and the test set. So we are going to go to MNIST. So Torch Vision has, let me see if I don't misspell anything, as a folder called datasets, right? And in these datasets you can find the MNIST. And you need to give arguments. We are going to put the MNIST in the temporary folder. We are going to give specific transforms. So there is a thing about these data sets that the resolution is 28 by 28, and for the ResNet 18 we need a bigger resolution, so we are going to resize the images. So Torch Vision dot transforms. We're going to do multiple transforms, so we're going to say compose, and now we give a list of transforms. So Torch Vision transforms, we are going to first map it to the shape that we desire, so 64 by 64, and we are also going to map this to a tensor. Let me see if this runs well. Torch Vision has no attribute to tensor, of course. It's Torch Vision.transforms. Okay, so we are going to say it is already downloaded, but for you to run it on your computer, you need to say that you're going to download it. This we download it to the temporary folder, so you don't need to delete it. If you reboot the PC, it will not stay in your OS system. And this basically is downloading the dataset of MNIST, the train set. So we're going to call this the train set. We're going to do the same for the test set. Okay, so we're going to say here in train equals to false, and just change the name of our variable. So now we have the train and the test set. We are going to define the train loader and the test loader. So we're going to say that this is from the Torch, utils data. We have the data loader there. It's going to be pretty basic. So you need to put the data set, of course. Specify a batch size. Let's say that we are going to use 1024 for batch size. And in the training, we always like to do shuffle. So shuffle equals true. This runs. Great, and do the same for the test set. Okay, Now, we are going to define the model. So the ResNet 18 that we imported here, okay, we are going to, this is going to receive, so let me just first show you how the init function works. So if you run the help command here, you'll see that the init function for this model receives a front-end ResNet, so this is still research that is being developed. You need to specify the number of filters. 0 does not work, so you always need to specify. And we recommend using the number of feedback filters to be higher or greater or equal to the number of classes of the problem. Registers, these can be 0, you don't need to touch it. The number of classes of the problem, so 200, this is for the tiny ImageNet. In our case, for the MNIST, we have 10 digits. The shape, so the resolution of the images, and the temperature of how the recurrency is going to evolve in time. Okay, so given this, we are going to we're going to specify the FB filters. We are going to say that it's going to be 16. I like it to have it in bases of 2, okay? So 16 is a base of 2 that is greater than 10. We are going to say that the number of classes is going to be 10. The shape is 64 by 64, so it's unchanged. So remember that MNIST says 28 by 28, but the reason we are resizing to 64 by 64 is because the ResNet needs a higher resolution than 28 by 28. And the temperature can stay the same, 1 as the temperature. We run our model. So I guess something is wrong here. Yeah, I didn't put an equal here. Okay, so the model is instantiated, and we need to do one thing. Okay, so in the ResNet you have the first layer, which receives an image with 3 channels, and in the case of MNIST only has 1 channel, so we need to change this, and we are going to hard code it and say that this is going to be a new convolution, so convolution 2D. So I'm just going to copy paste it from what I have in the original file. So the kernel size is the same as before, so 7 by 7 as we see below. The stride is 2 by 2. The padding 3 by 3, and we are not going to have a bias. Okay, perfect. So this runs. In our implementation, we need to do one more thing. So we have an attribute called frontend, and this frontend is going to be the composition of various layers. Okay, so we need to say that it's going to be sequential of model conf 1, model batch normalization 1, model relu for the activation, and model max pool. Okay, so these are the first layers that make the block of the ResNet. Okay, so if you run this, it's okay, perfect. So now the model is able to receive images with 1 channel of representation. And before starting to train, we need to define a loss function. So the loss function for this task is going to be the cross entropy. So torch-nn cross entropy loss. Okay, we are going to define an optimizer. Let's say Adam with a learning rate of 0.01. I think it's acceptable. And what more do we have? We don't need to specify anything else. So this is pretty basic. Okay, this is not. It requires the model parameters, of course. I always forget about it. I don't know why. Parameters. Yeah. And now we can start the training. So we're going to run this on a GPU. So we have a GPU with 32 gigabytes. So let's say that the model is going to go to the code 0. Now we need to define the whole pipeline for the trainings. Let's just do one epoch. Okay, I don't want this video to be too long. So we're going to run for one epoch. We are going to decompose the batches that come from the train loader. Perfect. And inside here, we are going to first say that X is going to go to the GPU. The same is going to happen to the target. So the target is the label that is associated to it. Then we are going to set optimizer.0grads. Some people like to do it different ways. I like to do it before the forward call. Loss function of the model X. Okay, and remember that deep feedback models can have an arbitrary number of iterations. So let's say that we set 5 iterations for this, and the way you set the iterations is in the forward call by saying how many T's do you want, and of course this is going to be compared to the Y. And yeah, okay, so after this we have the loss, we do backwards to initialize the gradients, we do optimizer step, so this updates the gradients. And I think we can do some prints here just to see how the program is evolving. So let's say that let's just put a key batch I, it starts 0, batch I plus equal, so increment for every batch that we process, and let's put a print here. So let's first print the loss. Okay, let's print the batch that we are at. So we set 1024 batch size. Okay, and let's just put here a comment that separates this, and also let's say at let's say loss at batch, and then we do this and just print the length of the train set. Okay, I think this is it. Let's just print things like this and separate per epoch. I don't do this if it's just one epoch. I think it's fine. Okay, let's see if this runs. We have an error. Element 0 is not required and does not have a grad function. So what is happening here? X. Okay, could a 0. Okay, let me just see what is happening. So maybe it's the Y. Let me first just print what is happening here. XY. So it's a tensor. Does not require grad, of course, and this also does not require grad. But somehow it's. Oh. Okay, I'm just gonna pause the video just to check what the problem is. I'll get back to you shortly. Okay, so sorry. Apparently, I had 2 Jupyter Notebook sessions running, and somehow I was still connected to the previous one. As you can see, the code is the same. I didn't change anything. I just connected to the correct port. So I have the previous notebook here where I terminated the session, and I connected to the one that I was supposed to use, but I really don't know what the error was. But okay, so let's run this again. Actually, I'm gonna remove this print because now the model is gonna start the training session. So let's turn it on. Okay. So it's still running in the beginning. The imports take a while. But yeah, I think if you understand this example, I think you are able to run these types of models in any dataset that you want. So I think it's really nice that with the MNIST dataset we need to first convert the int channels. So in your problem, if you have 1 or channels that are different to the number 3, of course, you can change these however you want. And this line right here is only needed for the sequential model, of course. And so then you just need to define the correct loss targets and your optimizer. Of course, you can do a lot more stuff here if you want to do regularization and other types of techniques. You can change this here. Of course, you can also play with the batch size that you are using, and there's a whole world about the transforms that you do for each batch in order for your model to converge to a good value. Okay, let me just check again if my connection went bad. Okay, so welcome back. We had a few, I think, internet problems. The Jupyter Notebook session was not building the connection to the server. But now we are training. Okay, so the code was correct. The only problem was with internet connection here at INESC-ID, which was not very stable. So as you can see, we are printing, the first number that we are printing here is the loss, okay? And here we have the tracking of which batch we are at. And yeah, basically Minis is a small data set, so in the sense that the resolution is small. But with 60,000 instances, I think this is very close to the size of the tiny ImageNet dataset. But yeah, we'll just wait for it to finish the first epoch. It's running quite slowly. I think that because there's some load on the server right now, but it's not that horrible. Yeah, so we can see that the loss is smaller and smaller for each batch that we process, and I think we can start coding the evaluation. So for the evaluation, I'm just gonna print the test set loss. So we have defined before a test loader, okay, and what we are going to do right now is that we are going to accumulate the test loss in a variable. Wait. Oh, weird. It indented. We are going to iterate through the test loader like this, and we are going to increment the test loss. So the loss function that we have defined, which is across entropy, we are going to say that the model is going to receive an X. We need to be careful because we need to map this X. We need to put it in the GPU. So code 0 is the one that we are using. And we are going to say, let's say that we are going to run it for 10 iterations. It's going to take a little bit longer, but I think it's worth it to demonstrate to you how this works. Okay, so the device, this also needs to go to the GPU, and we need to convert this to an item, and yeah, that's it. Let's see how long it takes. So this is double the iterations that we have used during the training set, and as you can see, this is the test loss. We can run the same for the training loss, and you can also compute accuracy and other types of metrics. But I just wanted to show you how to train a deep feedback model. And I think the only thing that changes in comparison to the other models is you have to specify the number of iterations that you are running it for. Okay, and of course this comes with penalties in how much memory you consume on your GPU. Of course, that you can make a trade-off and specify a batch size that is smaller in order for it to fit in your specific computer. But I think it's a good example to have and to extrapolate. So please, if you have any questions on for a specific application, please feel free to publish an issue on GitHub or send me an email. My email is david.calhas@tecnico.ulisboa.pt. So please feel free, and I hope you like this video. See you soon.